Good morning, students. Today's lesson is all about earthquakes and really going over the parts of an earthquake, the waves, how they're recorded. Let's jump right in. What an earthquake is exactly. It's when the earth is releasing stress. And that stress is released kind of all at once. So, the effects are dramatic and it's felt. You can actually feel the ground moving. This GIF right here actually shows the buildup of stress along what will become, a fault. So we can see there's the buildup of stress. You can see the fence. You can see the trees. The stress builds, but only to a point, and then the ground breaks, and that's the actual earthquake itself. It's the breaking of the ground, and it's the energy waves that are then given off everywhere. And really, just to kind of dive a little deeper into this, rocks under stress will change shape. That's how that works. And the word for changing shape is called strained. So in this diagram here, we can see that, as the stress goes up, there's also a change in shape. So the stress causes a change in shape. This is something that you can easily demonstrate with even like a ruler, for instance. If you have a ruler in your hand and you apply stress to the ruler will change shape. Or even like a pencil, or anything that you can think of that can, you apply a force, you apply stress, it will change shape. So the more stress that's applied, that's, more strain, more change in shape. But here's the thing though, any material, including rocks, there's a limit. So if we look at this diagram again, we have this place here where we're adding stress, we're changing shape, and then when we add even just a little bit more stress, you now cause a great change in the shape. So there's a huge increase in the changing of the shape with just a little more stress, and then you get to what's called the failure point. And the failure point is, what it sounds like. The rocks fail, the material fails, it cracks, and in that moment, the energy that was built up, all that stress that was built up in that changing of shape is released all in one moment. So here you can see this is the fault line. This is the place where the earth cracked and slipped. In this case, it slipped down. So there's like a small little clip here. And the place in the ground where the earthquake actually occurred, that's called the focus. And if you draw a line from the focus to the surface of the earth, that's called the epicenter. All right, so it's the point on the earth's surface above an earthquake's focus. We've seen these maps before. I'll show you one more. This is 358,000 earthquake events from 1962 to 1998. I hope it's abundantly clear where the plate boundaries are, because the earthquakes are really showing that very nicely. That is not to say that earthquakes can't happen inside of a plate, because by all means, especially in the United States, there are plenty of earthquakes that happen inside of a plate. But you can see the major concentration, especially in the eastern hemisphere here. We just see so many earthquakes, and we see that nice pathway that's showing the plate boundary really quite nicely. All right, so earthquakes actually make four types of waves. There's body waves and surface waves, but we're only going to go over the body waves because they're the most important in terms of the regions. And that's what we should focus on. So the type of waves, P and S waves, you might remember this from 7th grade because you probably learned a lot of this in 7th grade as well. So P waves are primary waves, primary meaning they come first. So when an earthquake is felt at a location, the first wave that's felt is the primary wave. That's because it travels fast. So it's the faster of the two waves. It can travel through solids, liquids, and actually P waves can travel through gases as well. But in terms of the Earth itself, it can pass through solids and liquids. S waves are secondary waves. They're slower, And they can't travel through solids, and we're going to go over why that is. It has to do with the wave itself. P and S waves are recorded on a seismograph. On a seismograph. So this is an actual machine that's bolted into the earth. And as the ground shakes, the machine itself shakes. And you can see this little needle point here. It's got a little pen on there, pen or pencil. And it records the back and forth. It records the shaking as a squiggly line. And that squiggly line is right here. It's called a seismogram. So a seismograph records a seismogram. And you can see the seismogram here. This is before the earthquake arrives. Then, okay, P wave arrives. We have shaking, 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 shaking. You can see the time that has gone by. And then the S wave arrives. So there's a clear difference between when the S and the P wave arrived. And that's going to become monumentally important later. This is what a P wave looks like. A P wave is also called a compression wave. And if you've ever been, hit by someone, maybe someone punched your arm or anything like that, that's a compression wave that they're kind of putting into your body. It happens by compressing the material, and the compression moves through the material very, very fast. This is showing it in slow motion. And so the direction of the propagation is this way, it's going forward, and the particle motion is back and forth. S waves are totally different. An S wave is an up and down motion. So the particles move up and down. And if you had to guess which of the two waves is more destructive, just by looking at it, that's a P wave. And that's an S wave. You might ask yourself, which of these is more powerful? Well, this S wave is doing some really crazy motion here. It is definitely the more powerful of the two waves, but it is slower. It's much slower. This is what a real seismograph looks like, and these are the real shakes that are recorded. The squiggly lines on this seismogram. We already said this, but the P wave always arrives first, and the S wave arrives second. You can clearly see the difference in the squigglies. That's evidence that the S wave is much more powerful. Alright, to kind of finish this up a little bit. So, we talked during the very first lesson about the Earth's layers. And I also mentioned that we've never been down there. We can't really get inside the Earth. So how do we know there are layers? Well, this is exactly it. We know there are layers because of how seismic waves, how earthquake waves, you understand how they travel through the Earth, and if you do a bunch of math, you can start to figure out what the inside of the Earth looks like. So you can see that these P waves, as they travel through the Earth, they actually bend. They all bend. Especially when the waves travel from one medium, like a solid. When they travel through a different medium, they refract. The waves themselves bend. And that leads to shadow zones, or areas where there are no P waves recorded. Right, that's some evidence that inside the Earth there are different materials, and especially different states of matter. And really the direct evidence that there is a liquid outer core is the fact that we know S waves, through experimental studies on Earth, we know that S waves cannot travel through liquids, and we also see that in the data. So if an earthquake were to go off over here on the Earth, as those S waves begin to travel through the Earth, they refract. But there's a whole section of the Earth here, almost one half of the Earth, that does not experience any S waves. And the reason for that is because there must be a liquid inside the Earth that is preventing those S waves from traveling through. That is how we make our inference that there is a liquid in there. There are many other things. There's many other observations we can make to confirm that, but this is a big one. The S waves are not recorded, and that's an indication that there must be a liquid that's in the way. All right, so measuring earthquakes. There's the Richter scale, and it's really measuring what's called the absolute magnitude. It's measuring the pure strength of an earthquake. And something to keep in mind, for every Richter scale level that you go up, it's going up by 10, 10 times stronger. So if a magnitude 7 occurs versus an 8, versus a 6 and a 7 occurring, that's a huge difference. A 7 to an 8 is jumping by 10. A 6 to an 8 is jumping by 100. Or a 6 to a 9. 9s are very rare. That's going up by 1,000 times. Again, every jump is 10. So you can also see here how often they occur. So magnitude 1s are occurring essentially all the time, every minute of every day, and we can't feel them. They're just way too small. Magnitude 4s, same thing. They're every day. Okay. Once you get into the really, really powerful ones, they really don't happen very often at all. There have only been a couple of magnitude 9s. The most recent one was in Japan, a 9.0 that occurred out off the coast of Japan. Very, very destructive. And just to kind of put earthquakes into perspective with other forces on Earth, here's your kind of average. Well, actually not your average, but here's a nuclear weapon. Actually, that's kind of a weak one. Let's go to the world's strongest nuclear test. The USSR. I think it was the Tsar bomb. A Tsar bomb is about an 8 magnitude. All right, so when we're talking about earthquakes, 8 through 9, 10 are much more powerful than that. The most powerful earthquakes here, Japan 2011 was a 9. Chile was the most powerful, a 9.6. Look how many more times powerful it is than even the most powerful nuclear weapon on the planet. Right? We're talking about just an unimaginable amount of energy that can be measured in, the trillions of pounds of TNT, of explosive. So earthquakes are harnessing immense amounts of energy. There's also the Mercalli scale. And the Mercalli scale is measuring earthquake destructiveness by measuring earthquake magnitude by damage. And the problem with that is if there are no buildings around, if there are no structures around, there are no roads, no people, then it will seem as if the earthquake is not strong at all. If a magnitude 9 were to happen in the middle of a desert, what's going to happen? Like a sand dune's going to fall over? What's going to happen? Nothing. Whereas if a really small earthquake happens in a city with some buildings, those buildings might fall down and people might say, oh my God, this earthquake was so powerful. Meanwhile, it wasn't powerful, just the buildings were weak. So the problem with the Mercalli scale is that it overestimates the strength of earthquakes in urban areas because there's just literally more to break. And it underestimates the earthquake strength in rural places where there's just, nothing to break. All right, that's it for today's lesson. I will see you all tomorrow.